Hi, my name is Alec from the WCU Department of Chemistry, and in this video I'm going to go over the density of air lab and some post-lab calculations. The first post-lab question asks you to perform the calculations needed to determine the density of air. To do this, we'll take the mass of the sample of air and divide it by the sample's volume to get a density in grams per liter. In our case, the sample's volume is equal to the Erlenmeyer flask you worked with. This is what the Erlenmeyer flask looked like. It's sort of this funky shaped piece of glassware. And the volume is not the number that was written on the flask, but it's the amount that is in the entire container up to the brim. So to get the sample's mass, you'll take the mass of the flask with the air in it, that's the combined mass that you weighed, and you'll subtract the mass of just the flask. And if we do that, we end up with the mass of our air alone, which is just those blue particles, and that's what we want. We just want the mass of the air. So to get the mass of the flask that held your air, you will take the mass of CO2 gas that was in the flask. We added a little pellet and it sublimed into gas. You'll take that mass and subtract it from the mass of the CO2 in the flask, which you weighed out. And once you do that subtraction, that will give you the mass of the flask alone. And so now you'll know the mass of your flask. Okay. As you undoubtedly recall from lecture, the ideal gas law goes like this. PV equals nRT, with P being the pressure of the gas in atmospheres, V is our volume, N is the number of moles, R is the ideal gas constant, and T is the temperature in Kelvin. So pressure for this, we're going to say it's 79.8 torr. And this should have been given to you in lab by your TA, but in this case we're just going to say it's 679. It is going to be less than 760 because we are not at sea level. V is our volume. This was a measured amount, so this should be from your data. I'm just going to write data because this was a measured amount. So we measured that one out. N is our unknown. This is the number of moles. This is what we're trying to find out in this part of the problem. So this is the that's our unknown. We know R is a constant. This is the ideal gas constant. It's 0.08206, something around there. And the units for that are, I would write them here, but we're running out of room. The units for that are liters times atmospheres divided by mole Kelvin. And if you find different units online, well, that's probably for a different equation or different situations. So this is the one you want, the one with liter atmospheres, mole Kelvin. And then temperature should have been measured in lab. This is also from your data, but we'll say it's 20. Sorry. We can say it's 28.9 Celsius, but remember you have to convert that to Kelvin for the ideal gas law to work. Before we can plug these numbers into the ideal gas law equation, we first have to convert them into the appropriate units. Now remember, these are just example numbers that we're using. These are not going to be related, or these are not going to be the numbers you can use directly in your lab. These are just the ones for the example. So, starting with our conversion of the pressure, we can convert our torrs to atmospheres using the conversion. We know there's 760 torr in 1 atmosphere. So when we do that, you can do the math and you'll get 0.8945 atmospheres. And now we're in atmospheres, and that can be plugged into our equation, and then the units will cancel out. So we do that, and these go like this. Sorry, I forgot that. And those cancel out. And then to convert our milliliters into liters, we said the volume of our Erlenmeyer flask was 549.2 milliliters. We know that there's 1,000 milliliters per liter, so then our units cancel, and we end up with 0.549 liters. Those can be plugged into the PV equals nRT now because they're the correct units. And then lastly, we want to just add our, sorry, this should be a plus sign. Lastly, we just want to add 273.15 to our 28.9 degrees Celsius. So we do that, and we can convert from kelvins, or excuse me, convert from degrees Celsius to kelvins. That'll give us 302.1 Kelvin. And now we've done all our conversions, so everything can just be plugged back into PV equals nRT. Now that we have our numbers in the right units, we can plug them into the ideal gas law and solve for the number of moles N. So if we plug in all our units, and note this is just a rearranged version of PV equals nRT, just divide both sides by RT and you can get to the equation shown there. So we have N is equal to, if you do the math on this, 1.982 times 10 to the minus 2 moles. And so if you look, all our units cancel out nicely. You see the atmospheres are canceling. We have liters that cancel right there. And then the mole Kelvin, remember when you divide by a fraction, the denominator goes up to the numerator, or you could just look at it right here and cross them out like that. So that's why we end up with moles. Once the number of moles of CO2 gas is known, we can use the molar mass of CO2 to calculate how many grams are present. So we just found out that there is 1.982 times 10 to the minus 2 moles of our CO2. That's what we just calculated from PV equals nRT. So then using the molar mass, we can convert this, because we know that there's 44.01 grams per mole of CO2. And so moles cross out, and we end up with 0.8722 grams of CO2. Recalling the reason for calculating the mass of CO2 in the flask, it was to help us determine the mass of the flask we used to hold our sample of air. This is done by simple subtraction. If, for example, the flask weighed 124.15 grams, then we can subtract the mass that we just calculated for CO2 alone, which was 0.8722 grams. We can do a subtraction, and that'll give us the mass of the flask alone, which is 123.279 9 grams. Okay, so we can now use this information to determine the mass of the air inside the flask. The flask weighed, for the sake of this example, we're going to say the flask weighed 123.858 grams, full of air, so this is the mass of the flask and the air inside it. And then we just found out that the mass of the flask alone was 123.279 grams. And if you do this, it comes out to 0.579 grams of air alone. So this is the mass of just the air now. At last, we can use the mass of the air to determine the density of air. Since the density of anything is its mass divided by volume, we can take the mass of our air sample, which we just found, and divide it by the volume occupied, which again is the volume of the flask, which you can measure from lab. In our case, we just determined that the air inside the flask weighed 0.579 grams, and then we're going to divide by our volume, which for our flask was 0.5492, and this is going to be different than the volume that you found during lab. This is just ours. And if you do the math on that, you'll get 1.05 grams per liter, and those are the proper units. So you'll do this calculation 3 times from your data for all 3 trials. Since you only measure the room's pressure and flask volume once, then you can use the same pressure and the same flask volume for each calculation. Then you'll average your densities and calculate the standard deviation for the post-lab question 2. So let's say, for example, our average was 1.03 grams per liter, and our standard deviation was 0.07 grams per liter. And remember, our standard deviation is the same units as our average. So using those values, we can go back to our scale and say that this is 1.03. And again, this is in grams per liter, but I'm not going to write that down. I'll clutter my space. And then if I wanted to do, to show the range, I could add 0.07 to 1.03, and that would give me a value of 1.10 grams per liter. And then to do it on the other side, to get your negative sigma value on the range, you would just subtract 0.07 from 1.03, and that would give you 0.96 grams per liter. And so then let's just say if I looked up the value, I looked up a standard value for the density of air, and the standard value was 1.2. Well, then I would go back to my range, and I would say, okay, this is where 1.2 falls. It falls outside of my range, and so therefore it is significantly different from the value that I found. So I hope that was helpful. Again, this has been Chem 105, density of air, the post-lab calculations. I'm Alec from Washington State University, Department of Chemistry. Hope you guys had fun.